So moving into bond polarity, we have to understand that with bond polarity, we're going to be using these electronegativity charts. We'll actually provide this chart for you. You don't need to memorize the values. The general trend we see will increase going up and to the right is where we generally see an increase in our electronegativities. Yeah, it doesn't always follow the trend perfectly, but that's our general trend we actually see. And we'll provide this chart for you on the test, so you don't have to memorize it. So bond polarity, we're going to break it down. We've talked about ionic and covalent, but we're going to kind of break this down and kind of throw a third one in there, kind of in between, right in between the ionic and covalent. So the first one, straight up covalent, is nonpolar. Nonpolar is what we call pure covalent. The electrons are shared, and they are shared equally. So this is the only time you'll get a 100%, and it is 100% covalent in character, 0% ionic in character in this situation. So the difference between the atoms' electronegativity will add up to 0. So I have hydrogen minus hydrogen. So we're going to be subtracting the electronegativities. But so you see any of your diatomic elements, you know right off the bat they have a bond polarity of 0. They are truly, purely covalent because it's one, again, the electronegativity values are exactly the same. Now we're going to also see another trend here that we see that we're 100% covalent and 0% ionic. These are directly linked together. So as we become less and less covalent, we're going to see that we start to become more and more ionic. But we never will get to the point where we become 100% ionic and 0% covalent. Covalent always keeps its foot in the door and always assists. Even with the strongest covalent, with the strongest ionic, covalent is still present, assisting with the actual bond. Again, so they're not enemies, they're just two different ways of forming a bond because the overall element needs to reach a point of, or compound wants to reach a point of stability. So this is, again, truly, again, covalent. So we see the electronegativities. I looked them both up. Hydrogen is 2.1. 2.1 minus 2.1 is 0. So that is truly covalent, nonpolar covalent. Now bond polarity, if they're bond polarities, now once they're unequal, and so what I will say, the books kind of teach it differently. They'll say maybe a 0.4 up to a 2.0. I really say this, is that once you have any difference in electronegativity, someone's starting to win and someone's starting to lose. Because electronegativity means the pull, the want, the attraction. So it's actually pulling. One of the higher electronegativity will win the tug-of-war match, in other words, when it comes to the electrons. So when the electronegativities are different, someone's winning, therefore they're unequally. But if they're still sharing it, they haven't reached a breakout point. Well, the breakout point is 2.0, less than 2.0. So 2.0 or less, when they hit that, actually it's less than 2.0. So 1.9 down to 0.1 is kind of a bracket I run and say if you're greater than 0 but less than 1.9, therefore you're going to be what we classify then as polar covalent, because you are going to start to create charges here, but yet you're still sharing it. You're just sharing it unequally. We can see this with HCl. In this situation, hydrogen is a 2.1, my chlorine is 3.0, a difference of 0.9. Therefore, it falls within the 0.1 to 1.9 ratio. Therefore, it classifies as polar covalent. When we write it out, we'll actually see that it is lopsided. Why? Because the chlorine has a higher electronegativity, therefore is pulling the electron more than the hydrogen is. So in this situation, it is pulling more, yet it's not taking it completely away from the hydrogen yet. So it's still in the process of sharing. In this situation, we'll also start to draw polar arrows. The only time we draw polar arrows, we're with the polar covalent. As you can see on the left-hand side, you kind of have a positive sign there, and moving the arrow, arrow always goes in direction towards the higher electronegativity. In other words, where are the electrons moving? They're always getting pulled by the higher electronegativity. That number is winning the tug-of-war match. And so my hydrogen is becoming more positive because it's losing, and my chloride is becoming more negative because it's gaining. So I start to create charges here. I will have a partially positive charge on my hydrogen side, and I have a partially negative charge on my chlorine side. So in this situation, we have electrons are transferred from one atom to another. Is now referred to as the third type, which is ionic. Now there's a complete transfer. When their difference of electronegativity is greater than 2.0, that's when we finally classify it as ionic. Now, is covalent still present? Yes, it is. Covalent is still playing a part in this, but the primary force involved in this bonding is anionic force, and it's the rule of 2.0. And so we see their difference because it's greater than 2.0. We have a difference there. Now when we draw out the formula, it's not overlapping because it's ionic, but we see that the cation gets smaller and the anion gets larger in forming this ionic compound. What type of bonds are in the following? Well, we actually take a look at this. We have Kf. We have potassium as my 0.8. My fluorine is 4.0. And the difference is 3.2. Therefore, we call it ionic. HBr, my hydrogen is 2.1. My bromine comes to 2.8. The difference is 0.7. Therefore, I call it polar. When I see bromine, any Hopf wrinkle, it's going to be this one itself divided by itself. So 2.8 minus 2.8 is 0. It is truly nonpolar. H2S, again, I have hydrogen on either side. Just focus on one hydrogen and one sulfur at one time. And we can say that we can then compare the same for the other bond as well. But between a hydrogen and a sulfur, the difference is 4.0. Therefore, we call it polar covalent. And you can just call it polar. So we call it nonpolar, polar, ionic. And then cesium and chlorine. Cesium weighs in at 0.7. Chlorine is 3.0. It's a difference of 2.3. Therefore, we classify it as an ionic compound. Remember, we give you the electronegativity chart, so you don't need to memorize it. Now, like I told you, as you become less and less covalent, you become more and more ionic. But again, at no point will you become 100% ionic. And if you look at the bottom right-hand corner, you see fluorine covalent. It is 0% covalent. So, excuse me, 0% ionic, but it is 100% covalent. Yet, as we move up the triangle towards lithium fluoride, we become greater. Our ionic is becoming greater and greater and greater. What that means is my covalent is becoming less and less and less, because covalent and ionic will always add up to 100%. So even when I get the lithium fluoride and it's at 80% ionic, the fact is it's still 20% covalent. So covalent still has its foot in the door and assisting with the overall bond. Remember, they're not enemies of each other. There's different types of bonds with the goal of reaching a point of stability.